Welcome to another episode of the Corrosion Journal interview series. My name is Sammy Miles, the Managing Editor-in-Chief of Corrosion Journal, AMP's peer-reviewed scientific journal. Today's episode will discuss corrosion life predictions, the topic of our March issue. I'm joined by Narazi Sridhar from MC Consult LLC and Chris Taylor from DNV, who served as editors for the issue. Thank you for joining me today.
Thank you for inviting us.
Yes, thank you.
So to get us started, can you provide a little background about yourself for our listeners?
Okay, I worked at DNV for the last 13 years, and after that, I retired from DNV and started my own consulting company called MC Consult LLC. I'm also an adjunct faculty member at The Ohio State University, and I've been in the corrosion field for the last 45 years or so.
Wonderful. And how about you, Chris?
Yeah, I'm Chris Taylor. My story will sound pretty similar to Sridhar's. I've worked at DNV since 2013. Sridhar actually hired me to join when he was managing the research and innovation group there with a focus on materials, technologies, and lifetime prediction was actually in scope of a lot of things we were looking at the time. My background's in computational material science and computational chemistry, and I continue to work in the Materials Technology and Development Lab at DNV in Columbus, Ohio.
So our March issue is dedicated to the 2022 AMP Research Topical Symposium, which is also known as the RTS. For those not familiar with the RTS, the symposium is held at AMP's annual conference, bringing together corrosion researchers and practitioners with common interests and featuring invited talks from leading experts. So why life predictions?
I think the fundamental reason, of course, is safety, because as corrosion engineers, we are responsible for the safety of not only the workers, but the general public as well. And so safety means timely management of any kind of failures to prevent any failures. And of course, the second reason is sustainability. So if you want to make systems sustainable, you got to make them last longer. And so I think life prediction is important for both of those. And I have to say that the last major life prediction conference was actually sponsored by the Legacy NACE organization back in 1994. It was there were two conferences put together that were major effort in this area. One was in Cambridge, England, and the other one was in Honolulu, Hawaii, and they were part 1 and 2 of those conferences. And anybody interested in life prediction will be inspired looking at those two books if they are still available. But that's kind of what inspired me to start this conference, even though this is a much smaller effort than that one.
So it's been just a little bit since '94.
Yes.
So I guess building on that, what are some of the topics covered in this issue? The special issue?
Yeah, I mean, understanding that the issue is finite in length and has some limited time frame for the RTS conference as well. But nevertheless, we addressed a wide range of subjects. It goes all the way from coatings to concrete. So there are topics related to how to manage corrosion in marine systems, how to manage cracking in offshore oil and gas production, managing fatigue crack growth in aerospace industry. There is a very nice paper on related to what the practical issues are in managing life systems of coated components. And Chris Taylor, my fellow participant in this podcast, has a paper that really links the atomistic aspects with macroscopic life prediction issues. And there is a paper on nuclear power plant as well. So the issue covers a pretty broad swath of industries as well as technologies in the corrosion area. I don't know, Chris, you may have additional thoughts on this, on what is covered.
Yeah, I would say that you've done a good job covering the topics that are in the special issue here. So
I guess broader than just the issue, what are some of the other areas and industries where studies are being done to improve lifetime predictions?
Yeah, I see that, when I look at the kind of research going on and the development in lifetime prediction and more generally modeling, materials degradation and trying to make some predictions, there's three kind of frontiers that seem to be emerging right now. One is around clean energy, which includes the work on the accident tolerant fuels and things that Sridhar spoke about, but also in terms of renewables and clean energy carriers like hydrogen, for example. There's a lot of work going on to try to address, okay, can legacy materials still be used for transporting hydrogen, for example, and what kind of lifetimes would we expect for those materials? Similarly, for carbon capture and transportation, there's some work being done there to try to assess and understand what are possible mechanisms that could affect the lifetime of materials, and can we make some predictions to help in designing for the next generation of the energy system. Similar things come up with PV and wind systems as well. Then there's transportation, aerospace and automotive. There's always new materials being developed, whether they're adhesives or polymers or coatings or different alloy combinations. And not only do we have to understand lifetime prediction of those materials, but is their lifetime modified when you're using them in different combinations with one another? For example, different ways of joining dissimilar metals. What kind of lifetime impacts are there on those things? And that's where we need to continue to be doing experiment and modeling, and then using ways to extrapolate from our experiments to what's happening in the field. And then there's sustainable materials themselves. As we look to recycle more metal alloys, for example, we're starting to get mixed metal streams, leading to some contamination and just different levels of materials quality that may need to be considered. And so again, when you're selecting a material, you want to have a knowledge of how long is that material going to be usable in your application. And so lifetime prediction is also expanding into those areas and industries as well.
Yeah, I think that's, I think you covered quite a bit of the green energy and the new application areas like carbon capture and storage. But even in the traditional industries, life prediction is still going on. For example, in refineries, corrosion under insulation is a major headache. And so there is a lot of effort going on in how do you predict equipment that are completely insulated so that you cannot see under the insulation very often. So you need to have an idea of what is happening so that you can take off the insulation and inspect them at the appropriate time period, because removing insulation and inspecting systems is extremely expensive. There are some other areas, for example, geothermal energy. There is a lot of effort now going on in using geothermal energy, especially in the western part of United States. And these are extremely corrosive fields. And so in order to produce energy from these geothermal fluids, you got to maintain them for longer periods of time. Otherwise, they are not economical. They are not cost competitive with fossil fuel if they break down all the time. And then another area that we should think about is, and people are already putting a lot of effort into it, is in biomedical devices. These are devices as we live longer and longer. A hip implant goes into the body, and has to stay in there for much longer than in the past. And same thing with active medical devices like defibrillation devices, incontinent devices. These are all very sensitive devices that are also very small that goes into our bodies. And so they, you have to make sure they last long. So I think the application is pretty much endless. Everything that our human society touches in some way, has to be maintained so that, we can operate society in an economical way.
I think that's the perfect segue into my next question for y'all. What are some of the challenges in predicting the lifetime of materials and equipment?
If I can take that question first, and then Chris obviously has a lot of insight into it. But obviously, one of the major issues, at least in some industries, is the lack of data or lack of appropriate data. So the industry may collect a lot of data, but a life prediction methodology may force the industry to think about the data that they are not collecting, but that are still available. So data collection and data storage are certainly an important challenge. The other one is knowledge sharing. And in some way, if everybody is developing a proprietary way to predict life, it's really difficult to share that knowledge. And in fact, one of the impetus for Corrosion Journal special issue is really to share the knowledge so that people can improve life prediction techniques. And then the last one, of course, is monitoring. The more monitoring we do and more sensors that we put in, of course, sensor technology it's in itself is a vast field and improving day by day. But if we can monitor things, then we can improve life prediction almost dynamically because we are predicting something, but we don't know whether it's right or wrong. And monitoring certainly helps us improve our prediction technologies. So I think those are the three major challenges that life prediction field faces. I don't know, Chris, any thoughts?
Really, sure. Yeah, I really love what you're saying about monitoring. I mean, monitoring does seem like it's kind of a, there are lots of opportunities for enhanced monitoring now with drones and sensor devices and things like that. But another one of the challenges with monitoring is, the point at which you're monitoring may not be the point at which you're having the most corrosion, right? So there's the stochastic nature of corrosion that sometimes it's just happening where you're not looking, right? Like one of those kind of problems where if you're looking at it, it's not going to happen. Like when you're waiting for the kettle to boil or the microwave to finish, right? It's like it's always going to be happening somewhere where you're not paying attention. And there's this idea of nonlinearity as well. Like if you measure corrosion in the lab for, say, you do a 2-month experiment, it doesn't mean you can extrapolate from that 2-month experiment, even though that's a long time for a lot of people. Oh, that's 60 days to do an experiment, but can you extrapolate that to 2 years, to 2 decades? Generally you can't, because you have some initiation time and then you often have some kind of propagation time. And then, you may get a crossover from one kind of mechanism of corrosion to another mechanism of corrosion, or you may transition from corrosion to cracking, right? There's all these kind of things which are explored within this special issue, which, just kind of reinforce this point that lifetime prediction is not a simple matter, and you have to devise your experiments carefully. Sridhar's talked a lot in the past about the different acceleration vectors that you can try to use in the lab, whether it's raising the temperature or changing the pH or increasing the chloride concentration or something to kind of stress test your material in a very quick way so that you can maybe screen out one material versus another. But how do you take that numerical quantitative outputs of those and translate it into a lifetime prediction is another challenge in and of itself. So there's that nonlinearity, possibility for crossing over from one kind of corrosion mechanism or degradation mechanism to another. And then there's the uncertainty quantification, right? So say you measure a corrosion rate within plus or minus, if you want to extrapolate that to twice the time period, your uncertainty band kind of can double or more than double. So then you're starting to make predictions that are not as certain as you're looking into the future. So that's where the kind of techniques that are explored in the paper that Sridhar has using Bayesian networks provide one way of taking your uncertainty and embedding that in the lifetime prediction itself. So you can say, oh, well, I'm 90% confident looking out to 3 years, but if we want to go to 5 years or 10 years, that band of uncertainty is increasing. There's a lot of work in the materials and other physical sciences to try to improve the way we do uncertainty quantification. And then the third thing is about the unknown unknowns, right? What are some things that may be happening in the future that we haven't currently planned for? And Sridhar brought up the topic of geothermal systems earlier. And that's a great case study because often over the lifetime of a geothermal well, it's producing, heated water, superheated water, but the mineralogy, you may end up moving to a very different pH or a very different kind of mineral acid from what you started with. So that's where monitoring, continuing to be knowledgeable about your process and proactively doing some experiments and looking into the possible space of problem actors can be helpful for lifetime prediction.
Yeah, I think that's, you make a lot of good points. Another point is Even if you can inspect a system, the question always is, when do I inspect next? I've done inspection this month. Do I wait for another 5 years, which is what is required in some pipeline regulations, or do I wait for 2 years? So there is a lot of discussion about this idea of condition-based maintenance, where you maintain depending on the condition of the system, so that you are not wasting resources doing maintenance too often, or you're not endangering somebody by waiting too long. And so for all this kind of issues, the condition-based maintenance, you need light prediction techniques. So I think it's fundamental to everything we do in the corrosion area.
Based on a couple things y'all just said, if you have a system and you inspect it and you're noticing that it's not in line with what your original lifetime prediction are, do you go back and model or forecast out, change the directory of what you've originally predicted? I worded that horribly, but.
No, I think that's an important topic. And this is in a way aligns with what Chris mentioned early on, is we do this modeling called Bayesian modeling. And the idea behind that is if you make a prediction and then you make an observation, you have to be able to go back and update your prediction based on that observation. So it's not that models are always wrong or that they are always right, that there is some uncertainty about the model prediction and you want to be able to correct it. So I think part of the effort is how do you make these corrections? And so there are now people thinking about various kinds of probabilistic approaches because of all the uncertainties involved, to make those corrections and improve the model as we go along. So ultimately the model gets improved as time goes by with all the data we collect. So that's an important topic as well that is addressed in this particular special issue.
Perfect.
And you talked about also what kind of advances are being made, and certainly leading effort in this is the multi-scale modeling. That especially that Chris's paper in this issue talks about multi-scale modeling, because you can take the data from a big system. Let's say you take the data from a pipeline inspection data, and you can build a database modeling. That's what a lot of the people now are talking about: artificial intelligence, neural network, and so on. So you collect all this data and you build a model, but that assumes that the pipeline system is going to behave the same way as what it had done in the past. You don't know that. There could be some new changes occurring in the process or the materials. So one of the approaches that that many people are undertaking is how do you build this knowledge from the atom up? Because if you can understand the real fundamentals of the process and then link it to a major macroscopic system, then it provides you an assurance that even if something changes, you can understand what is happening. And so that's a huge area of ongoing research in this particular overall life prediction scheme.
What are some other advances in lifetime predictions and how it's affecting changes in the real world? I say real world, or science, or technologies, or?
I think, like I mentioned before, artificial intelligence is now really in the forefront of everybody's thinking. Mostly people think about, open AI, chatbot, and those kinds of things. But those are mainly linking documents. And so essentially, it's sometimes linking documents in a weird way to say new things about other documents. But AI will improve over time. And potentially it has the capability of linking data in a variety of areas to make predictions on a system that you're interested in. In the medical field, AI is really improving ability to predict, whether you're going to have a heart attack or a cancer or what type of cancer somebody is going to have based on fundamental genetic data as well as lifestyle type of data. And the same kind of approach could come in handy for corrosion life prediction as well. And the other thing that is really needed, and I think things are going in this direction, is how do we share data in a way that everybody can use? Right now, I think we are somewhat compartmentalized for a variety of legal and commercial reasons. But how do we share data that we can then all use? So hopefully this corrosion forum that we have created through the journal publication will sort of push that need along.
Another thing that I would like to add is that I feel like there's also developments in the way that we do experiments with, the ability to do high throughput experiments. So an example of that is where, for example, Professor Schindel Holtz at Ohio State University has used an inkjet printer to print controlled amounts of different salinity droplets of water across a metal sample, and he can look at how the corrosion varies as a function of different environmental variables. So now when you can run not just one experiment, but hundreds of experiments on one sample, you can start to collect more data to drive these kind of data-driven modeling and lifetime prediction approaches. So we're continuing to do better with automation, things like 3D printing, which are really allowing new ways of doing experiments. Not only has machine learning and AI been applied to come up with new models and do data mining, but it's also being used to improve the way we analyze microscopic images from samples in terms of characterizing the role of microstructure or grain boundaries or other things related to, say, surface chemistry and corrosion products. So we're starting to understand a lot more about the experiments that we're doing and the information that we're getting from them, which can really help drive better understanding of the modes of corrosion, which then leads to better lifetime prediction models.
Yeah, I think that you mentioned additive 3D printing. A lot of these kind of new materials are going to also push us into thinking about how to predict life of the components made with additive manufacturing, because they use a completely different technology for manufacturing things. There are also a lot of advanced coatings coming into place because of these technologies. So I think there is certainly a lot of need to push the boundary in terms of these new materials as well from a life prediction point of view.
What are some other areas that need additional exploration or that are currently just starting to be explored, right? If you mention additive manufactured components or products, what other areas?
Yeah, I think there is one paper in this special issue by Raoul Rebec at GE that sort of alludes, it's a perspective, but it talks about accident tolerant fuel in nuclear power plants. So one idea is how do you predict the life of systems in nuclear power plant, but the other way also is how do you reduce the consequence of events like tsunami that happened in Fukushima, which brought in a lot of seawater into the reactor core. How do you make the fuel themselves more tolerant of accidents? So it's sort of the addressing the flip side of risk. You reduce the consequence. So I think there is going to be a lot of attention paid to sort of inherently safe systems, as they call it, whether it's a nuclear reactor or a power plant or even automotive applications.
Yeah, and I also wanted to add that, not only is lifetime prediction and corrosion management about trying to have, the longest lifetime and avoid any failure, but it's all about really understanding how does failure proceed in the material, right? Like we don't need every material to last 100 years, but we just need to understand how it's failing or how its mechanical properties or its ability to, resist corrosion are changing over time. So, it's not always about having something that's ultra corrosion resistant. It's just making sure it can be managed and understood in a safe and handleable way. And the other thing I thought was interesting about this special issue is some of the papers were not just looking at how fast does something corrode in terms of lifetime prediction, but they wanted to understand how does the morphology of corrosion change, over time. Do you have more hemispherical pits, or are they more ellipsoidal, or do they have some kind of structure that represents the way the material was machined in terms of these cross-hatching pits, as in the paper by Jay Srinivasan? And then similarly with the papers looking at environmental assisted cracking, sometimes it was the crack length that's maybe changing, or cracks are coalescing rather than just the crack depths propagating. So there's all these other features of corrosion that can be interesting to model and explore, not just trying to predict a corrosion rate over time.
I think that's a good point. It's not always that we want an extended lifetime. In some, for example, some biomedical implant made of magnesium-based alloys, you want a predictable lifetime at which the implant essentially disappears. And so there are all these other nuances to life prediction that we need to be aware of.
We're coming near the end of our time. So do y'all have any final thoughts before we wrap up?
Well, I think this is just the first step. I hope there are many more issues devoted to life prediction of other application as well as technology areas. So I'm looking forward to, other issues that are similar to this.
I would echo that. I know when I was growing up and started to get interested in science, I felt like all the interesting scientific problems would be answered already. But the more we learn, we realize that we're only just scratching the very tip of all these things. So much more to know.
I feel like that's the way it works though, right? The more you learn, the more you realize you don't know. And it just kind of propagates. So I want to thank both of you for joining me today. If anyone wants to follow up with you later, what's the best way for them to get in touch?
They can either look at my website, www.emcconsultco.com, or they can get in touch with me by email.
And likewise, you can look me up on LinkedIn, Christopher Taylor at DNV, or my email, christopher.taylor@dnv.com.
Perfect. And for those listeners that want to learn more about corrosion life predictions, go to corrosionjournal.org to read our March 2023 issue. And with that, I'm Sammy Miles here with Narazi Sridhar and Chris Taylor, and thanks for listening to another episode of Corrosion Journal's interview series. You can subscribe to AMP podcasts if you haven't already on Apple, Google, Spotify, and all the major distributors. If you want to learn more about the journal, make sure to visit corrosionjournal.org. You can find all episodes of AMP podcasts on amp.org. That's ampp.org. And we'll be back soon with another episode. Thanks for listening.